Well, hello again to everybody, and welcome to week number 3 here in our virtual classroom. This week I decided to start off the video by taking a picture of the fish that you guys should remember from my classroom, which right now is actually sitting in my living room. But I wanted to show you that, yeah, Pepsi's doing okay, and I actually miss having some of you guys around to do the changing of water and cleaning and feeding the fish, but it is doing well and staying healthy. Hopefully you guys are also doing well and staying healthy during this time. So the past couple of weeks, you guys have been learning about similarity. And you should remember that similar, which had that symbol that was the little squiggle, meant that you had things that were the same shape, but not necessarily the same size. The important thing about similar figures was that the corresponding angles, the angles that were in the same place, were always congruent, and corresponding sides were proportional. They always reduced to equal fractions. Of course, most of the problems you had last week amounted to setting up and solving proportions. And here, for example, you'd match up the biggest side of the first trapezoid with the biggest side of the second one, and I could set that equal to the smallest side of the first over the smallest side of the second. You cross multiply and you can figure out that x has to be 9. I did essentially the same thing and then figured out that y is 30. So again, you can always match up what goes together and find proportions. So this week what we're going to be doing is focus again specifically on similar triangles. Now, before we get into the idea of similar triangles, I want you to think back a couple chapters. And you should remember we learned earlier this year about rules that you could use to show that triangles were congruent. I know that there's lots of you like, oh, in my mind I could think specifically of Drew Casey, that could probably go through the little song and the dance to say things like side, angle, side, and all of the rules that you can use to show congruent triangles. SAS, SSS, ASA, and AAS. Those were the rules we learned earlier for why triangles could be congruent. Well, we don't have any Chinese kids to help us out in this chapter, but what we're going to talk about in the section today is some rules that you can use to show that triangles are similar. And they're actually fairly close to what we did with congruent triangles. The first of the rules that we're going to learn is called AA. And you notice when I put this, I put a little squiggle after it. That means it's the AA similarity postulate. Now, if you think about what we did back when congruent, your common sense ought to tell you that this is going to stand for angle, angle. And that is exactly what AA means. If you put it in words, what the AA postulate says is if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. As long as I have two pairs of congruent angles that I can match up, it's automatically going to guarantee that I'll have similar triangles. So AA, angle, angle, you've got similar triangles. Here's a picture that shows you what that would look like. In this picture, you can see that angle A and angle Y are marked to show that they're congruent. So are angle B and angle Z. So I have two different angles of one triangle that are congruent to two different angles of another triangle. And that's why I know that these two triangles have to be similar. I could say that angle ABC has to be similar to triangle YZX. Now, sometimes people will say, why do you just have to have two? Why isn't it three, like all of those congruent rules we learned earlier? And the reason is, if I know two pairs of angles are the same, I'd automatically know that the third one is too. That's because you could just subtract from 180 and figure out how big angle C is and how big angle X is, and they're going to have to be congruent to each other as well. So if two angles of one triangle are congruent to two angles of another triangle, then those triangles are similar. Here's three different pictures that are showing you how this postulate might work. At the top right, you see sort of a bow tie shape. There's some right angles that are marked to be similar. And there's also some vertical angles in that picture. And since I've got two pairs of congruent angles, I know that triangle QRS and triangle TRV would have to be similar. Same thing down at the bottom left. We have angle A and angle C, and then what's marked as A prime and C prime, the ones along the bottom of the big triangle and the bottom of the little triangle. Since those are congruent, then I know the big and the little triangle have to be similar. Now at the bottom right, nothing is actually marked in this picture, but it's really kind of showing you what's going on when we do have AA. If I did know that these angles were congruent, what basically happens is you've got a big and a small version of the same triangle. It's basically just like one is a scale model of the other. Now again, without anything marked, I can't say that those triangles are similar, but if I knew, for instance, that angle A and angle P were congruent and angle C and angle R were congruent, then yeah, those triangles would have to be similar. One of the kinds of questions you'll see will look sort of like this, where they show you a couple of triangles, and the question is simply yes or no, are these triangles similar? So look at that for just a second, and then we'll double check as to why or why not. Well, to apply that AA postulate, I've got to have two pairs of angles that are the same. I can see that I've got 102 in both of the triangles, but what I've got to do is figure out what's missing. And if I take 180 minus 102 minus 30, I can tell that angle G would be 48. Well, now that's the same as angle N over in the second one, so yes, these will have two pairs of congruent angles, and that means, yeah, by AA, they would have to be similar. On the other hand, if you look at these two triangles, these are not going to be similar, because here, if I take the first triangle and I subtract off what I know, I'd find out that the third angle is 39. And in order to be similar, it would actually have to be the same as the 40 that's over in the second triangle. Since it's not, there's no way that these are going to be similar. Well, AA is the first of three different rules that we're going to learn that you can use to show that triangles are similar. The second one is called SAS. And again, we have a little squiggle after it to show that we are saying that this is the SAS similarity theorem, not congruent. And what the rule says is if two pairs of corresponding sides in two triangles are proportional, and the angles between them are congruent, then the triangles are similar. So what in the world does that mean? Well, if you look at the picture I have here, if you look at the sides and match them up accordingly, I'm going to look at 27 and 18, the shorter side of the big triangle and the shorter side of the small triangle. If you look at 27 and 18, if I made a fraction out of those, 27/18, it's going to reduce to 3/2 or 1.5. Then if I go to 36 and 24, if you take 36 over 24, you're also going to get something that reduces to 3/2 or 1.5. I get the same fraction both times, so that's how I know that I have two pairs of sides that are proportional. In this picture, I also would have vertical angles at B in the middle. Angle ABE and angle CBD are going to be the same because they're vertical angles. And so since I've got two pairs of sides that are proportional and those vertical angles are congruent, I've got side, the angle in the middle, and then another side. That's what makes these triangles similar. Again, your pictures could look like a lot of different things. If I do the same sort of thing in these problems, I could look at the top and see, for example, that the sides in the larger triangle are again going to be 1.5 times as big as the ones in the smaller triangle. The angle in the middle of both of them is 50 degrees, so those have to be similar. Down at the bottom, you need to be careful of what you're looking at for the measures of the sides. Here I would have the shorter side, the small triangle, is going to have sides that are 4 and 2. For the big one, the sides actually end up being 10 and 5 because I have to add up to find out the whole length of the side for each of those. And here, if I look at 4 and 10 and 2 and 5, again, those are going to end up making the same fraction. We'd have the angle up at B at the top that's part of both of those triangles. So again, SAS, these are going to be similar. The question here says, why aren't these triangles similar? And I want you to look at that for just a second. If we were in class, I'd have you raise your hand and tell me, but see if you can figure that out. And if you look at it, the sides that are given actually do work out to be proportional. They'd reduce to 3/5, matching up small with small and large with large. But the problem is that on the right-hand triangle, the angle that's given is between those sides, but on the left, it's not the angle that's in the middle. It's a different angle that was marked to be 45, and it's got to be the same angle, and it has to be the one that's between the two proportional sides. So here, no, because the first one really is like SSA. You remember from before, if you turn that around, you get something you shouldn't say. That's going to end up being not similar. So far we've looked at AA and SAS. The third rule that you can use to show that triangles are similar is SSS with a squiggle after it. And of course SSS is going to stand for side, side, side. In words, what it says is if all three sides of one triangle are proportional to the corresponding sides of another triangle, then those triangles have to be similar. The thing you have to be careful of when you're looking at this is you have to match up small with small, medium with medium, large with large. So here, I would look at, for instance, 8 and 6. I put those together and see what I get. Then I would look at 12 and 9. And finally, I'd look at the biggest side of each of those, 16 and 12. Well, each of those, if you made a fraction out of like 8 and 6 and 12 and 9 and 16 and 12, they all reduce to 4/3. And so that's the same amount. We're going to have the same proportion all 3 times. As long as I get that same proportion all 3 times, that guarantees that we'll have similar triangles. Here's another question that's just asking, are these triangles similar? So again, let's look through that and see if you can figure out whether they are. And again, what you've got to be careful of is that you match up the right stuff, that the short side of the left one goes with the short side of the right one, medium with medium, large with large. And I divided up all of those and came up with 1.4 every time. 7/5 is what they'd reduce to. And so since that came out the same each time, then yes, these are going to be similar. If even one of them did not come out to be the same, it would be no. But as long as all three work out to be the same proportion, yes, this is going to be similar by SSS. The majority of the problems that you're going to do will show you some pairs of triangles and ask you, why are these similar? And it's exactly the kind of thing we were doing back with congruent triangles, except that you need to remember the three rules for similarity are AA, angle angle, SAS for side angle side, and SSS side side side. Those were the three rules you could use for show that triangles are similar. So that's your notes for this week. I have two different things I posted as assignments. One of them is a worksheet about similar triangles, and one of them are some problems from this section in the book, which happens to be section 7.3. You will, of course, have a quiz coming up, which, like always, will be due on Friday. So take care. Good luck with that. Hopefully you guys are all doing okay, and I'll be seeing you in another couple of weeks back at school.